In this session, we will discuss about the random variables and the introduction to probability distribution. Throughout this chapter, based on these 6 questions, it will be made up. First, we will discuss what is meant by a random variable, what are the different types of random variables, and we will discuss some examples for the types of random variables, and then we will see how we can define a random variable for a given statistical experiment. Here, 4 situations has given. Then we'll discuss them one by one, how we can define the random variables for each of these experiment, and then how we can identify whether the random variable is a discrete random variable or continuous random variable. And in the latter part of this session, we will discuss some definitions and notations for probability distributions, discrete probability distribution, and continuous probability distribution. And then we will see how we can define the mean, variance, and the standard deviation for the probability distributions, as well as here we will discuss about the how to identify the cumulative density function of a probability distribution as well. Since these are the things that we are going to cover up using this session, the random variables and probability distributions, now we will start from our first question. It is what is meant by a random variable. Now we will look on random variables. In statistics, random variables are used in the study of probability. A random variable x represents a quantity being measured. A random variable is just a rule that assigns a number to each outcome of experiment. These numbers are called as the values of the random variable, and random variables can be categorized as discrete random variables and continuous random variables. And then it is saying that we often use the uppercase letters to denote a random variable. It is given in these wordings what is random variable, and now we will try to have an idea regarding these random variables now. Okay. In statistics, it says that random variables are used in the study of probability. In statistics, one major concept used in statistics is this concept called the probability. Therefore, when we are going to discuss the things with the probability, we need to use the variable. Therefore, in such a situation, if you are using a variable, we'll let it as the variable x. If our variable is x, then this variable is said to be a random variable. This variable is generally saying to be as a random variable. If we see about what is actually mean by a random variable represent a quantity which is being measured. Therefore, apart from the theories of the probability, prior to the theories of probability, we have to first define this quantity x, or our random variable x. We can simply say that random variable represent a quantity which is being measured. This represents a quantity which is being measured. As an example, we can simply think in this way. Now think that if I am measuring the height of the students, if I need to measure the heights of the students, now we will have, there may be student 1, student 2, student 3, student 4, and student 5. If I write down the heights of these students, then we can say that for the first student, I got it is 170 centimeters. Then it is 156 centimeters, 167, 172 centimeters, 173, 69 centimeters. Likewise, we may have obtained some values for the heights of each student. Therefore, if you need to show these heights using a variable, then we can assign this the height of the students as our variable x. That is why we can simply say that a random variable represents a quantity being measured. Therefore, for the first two student, we can have that value of x is equal to 170. Therefore, then for the second student, x would be 156. For the next student, x will be 167. Likewise, for the last student, this x will be now equal to 169. With this example, you can see that there are several values, or there may be a set of values which can be assigned for the as the value of x. Therefore, we may have a set of values which we can assign for x, and this assigned value is the quantity that we have measured. That is why we can say that random variable represent a quantity which is being measured. And when we are having an experiment, we can define this as a rule. If we are having a rule which assigns a number to each outcome of an experiment, again we can say such situation as a random variable as well. Therefore, we can say random variable is just a rule that assigns a number to each outcome of experiment. Here we have done the same thing. We have observed the values for if we are having the experiment as measuring the heights of a student, if that is our experiment, and if x is the quantity which is being measured, then we can say we can have the values of x, and we are assigning the values for this quantity x. That is why we can again say that random variable is a rule that assigns a number to each outcome of an experiment. And if you are assigning the numbers for these variables, as an example, if you take the same example of measuring the heights of a student, now we can say that x has 5 possible values in this situation: 170, 156, 167, 172, 169. Therefore, we can say these are the possible values for the random variable x. These can be mentioned as the possible values for the random variable x. And according to these wordings, we can say that random variables can be generally divided into two categories. Random variables can be divided into two categories. Basically, this is the categorizing of random variable. The first thing is the discrete random variable, and next category is said as the continuous random variables. Therefore, there will be two categories: discrete random variables and the continuous random variables. Laterly, we will discuss about these discrete random variables and the continuous random variables in detail. But prior to that, since we are still at this step, defining on random variables, the next case is that we can use the uppercase English letters to denote a random variable. Therefore, as an example, to denote a random variable, we can use the uppercase English letters like X, Y, Z, T as P, Q, R, A, B. Likewise, we can say we can use the uppercase English letters. That is what we have to keep in our mind. Generally, we are not using lowercase letters to denote a random variable. We are just representing representing elements by the lowercase letters, and generally we are using uppercase letters to denote a random variable. Now we will discuss on the discrete and continuous random variables. When a random variable, we will say the random variable as x, can take only countable values such as 0, 1, 2, 3, then X is said to be a discrete random variable. If you see on this wording, in the previous explanation, I told you that random variables can be categorized as discrete random variables and the continuous random variable. Continuous random variable. Now, if you discuss on this discrete random variables, we'll see what is defined as discrete random variables. And when we are defining a random variable, I told that in the previous explanation, random variable can take values. Therefore, based on the type of the values that we can assign for a random variable, we are having these two categories. If the values that we can assign for a random variable is such as the countable values, it is quite as if you are having the number line in this way, we may have the values as 0, 1, 2, 3, 4. Likewise, if you are having the countable values in this form for the random variable, then we are saying such random variable as a discrete random variable. And if you look on these set of values, in between 0 and 1, there cannot be having any numeric value. In between 1 and 2, there cannot be any numeric value if it is discrete random variable. It is quite like this. Now think about if we are counting the number of students, if we are counting the number of students in a classroom. If you are having the number of students in the classroom, we may have it as 50, 51, 52, or likewise, and you say that it is 80, 81. Likewise, you may have these values. Now, if you consider these two consecutive values, now think about there are 51 students. Therefore, there will be a student having the number 50 and next student is number 51. If we are assigning it as a discrete random variable in between 50 and 51, there should not be any student. Therefore, in a situation like that, we can identify that if we are giving the numbers to students, then there will be a student having number 50 and there will be another student having number 51. In between this 50 and 51, there is not like a half of a student or quarter of a student. There is nothing like that. Therefore, in between these two, we can have, there is a clear cutoff in between these two. Then we can say such, if we are assigning such values to a random variable, then such a random variable is set as a discrete random variable. And now we will focus our attention on the continuous random variable. If we can assign the values for a random variable, let the random variable naming as X, and if we can assign an interval of values as an interval of values for this random variable, then this random variable is said to be a continuous random variable. It is quite like this. Now think on the measuring of a daily temperature. Measuring of daily temperature. We'll say X. The experiment is measuring of daily temperature. If you are measuring the daily temperature, now we can see that we may have the values, it may be 20, 21, 22. And if you are using the Celsius scale, Celsius degree scale for this measuring of daily temperature, now one day you may identify that it is 20 and in the next day it is 21. But if you see on this range 20 and 21, you may be able to identify the value as 20.5. In between 20 and 20.5, there may be a value such calling as 20.1. And if you magnify this small distance 20 to 20.1, there will be another value as 20.05. Then another value will be 20.01. If you magnify this small distance 20.01, there will be another point as 20.005. Now you may see that in between this 20 and 21, there are infinitely many values. Since we can see infinitely many values in this range, this can be considered as an interval of values. Therefore, if our random variable takes an interval of values, then such random variable is said to be a continuous random variable. We can have several examples on this for the continuous random variables, measuring of daily temperature. Suppose that measuring of a height of a student, if one student having the height as 180, then if you see on this 108, it is in between 79, and if it is 180, if you take this interval, then there will be finitely many more values. It is because it is not directly going from 179 and directly go upwards as 180, 179 and 180. This is not the way that we can see in a situation like this. If we are having 179 and 180, there will be a gradual increment. It is quite like it can be considered as a connecting line. Have to write this one. Now, if you see on if you are having 179 and 180 here, then 179 is the point is here, 180 point is here. If it is discrete, it is going in this way. It means it will be a sudden increment at the point 180. But if it is a continuous scale, then it will be having a gradual increment. The slope of this line may be varied, maybe sometimes a curve. It depends, but anyhow, we can see that there is a increment. It is because we cannot go at the exactly by 179, and then at a single time we cannot just move to 180 in temperature. You can easily identify this scenario. You cannot have the temperature from 23 Celsius to 24 Celsius at once. It is because there should be a gradual increment. Otherwise, there is nothing in this form. If it is 23 here, if it is 24 here, then there is nothing like this in the temperature. But if you are counting the number of students, until we are meeting the student number 24, we will have the count as 23 only. But if it is temperature, there will be somewhat a gradual increment. It may be it may be a shape of curve, it may be shape of line, and the slope of the line may be also changing according to the measurement we are taking. And now we will see for some examples related to this, how we can identify the random variable for a statistical experiment, and then how to identify whether it is a discrete or continuous random variable. Now think on the first statistical experiment. You are asked to measure the daily rainfall in inches. This is the experiment you are going to perform, and first you need to identify what is the random variable. Here I have let the random variable as x, and since you are asked to measure the daily rainfall in inches, then what you need to identify is you need to find out the amount of rainfall in inches. Therefore, it is the thing that you are going to measure. Amount of rain each day in inches, or amount of rainfall in inches for each day. It will be your random variable, since it is the quantity that you are going to measure out. And if you see about whether the variable is discrete or continuous, you can think in this way. Now think about you are measuring the rainfall, and you are measuring it in inches. Now think on having the inches, we will have somewhat less raining. somewhat training. If you are having 1 inch and here in the line we are having 2 inches, but in between this 1 and 2 there will be some many more values, infinitely many values. It is because the rainfall, if you are now think about, if you are measuring the rainfall, then if we are having this as 1 inch, if it is 1 inch, and this is the level that we are getting 2 inches. This is the level of getting 2 inches. Then is this going to this point just by a single move, or we have to pay the attention whether it is gradually increasing? It means that with the time this 1 inch may be become to this point, then it may comes up to this point. Likewise, we will have a gradual increment and we will have this the point 2 inches. Therefore, we can, since we can identify many more values in between this 1 and 2 inches, it is quite a continuous scale we are using. That is why we can say such random variable as a continuous random variable. Therefore, in simply measuring a length, weighing a person can be simply considered, or measuring temperature can be simply considered as examples for continuous random variable. And in the next, if you suppose the next statistical experiment as the counting the number of sewing machines in an industrial zone, here what we are going to do is we are going to have a count on the numbers of sewing machines in the industrial zone. Then we can have, if we are going to, if you need to identify the total number of sewing machines in the industrial zone, first we need to identify number of machines in the factory. Therefore, you are going to count, have a count for the number of machines in a factory. Therefore, here I have used the letter Y to denote the random variable and YZ to be the number of sewing machines in a factory. It is because that is the count that you are going to take, or it is the quantity that you are going to measure. And if you see about whether it is discrete or continuous, what you can identify is if you are having the number of machines. Now think about, if you are having 199 machines, then next machine will be exactly 500. There is no any machines in between these two values. Therefore, simply we can have this as a discrete random variable. If you move further on these examples, measure the weight of a set of machines in kilograms. Here also, what you are going to do is you are going to weigh machines. Then we can have random variables as weight of a machine in kilograms. And here the random variable is denoted as the letter Z. Since you are weighing, then we can have it as a continuous random variable. It is because weight cannot just moving from 1 kilogram to 2 kilograms. Therefore, there will be a gradual increment. You cannot just have this as exactly it is 1 and then it is going to 2. Therefore, there will be, here we can have an interval of values and we can identify infinitely many more values in between these two values. Therefore, this can be considered as an interval of values. That is why we can say this is a continuous random variable. Then counting the number of defective light bulbs in the case of bulbs. Here, since we are having a count, then we need to identify the number of defective light bulbs in the case of bulbs. It is the quantity that we are measuring, and since we cannot see any halves or quarters or 3/4 of these bulbs or the defective bulbs, then definitely if it is 1 and 2, there is no any value in between these two. Therefore, we can simply say it is a discrete random variable. Now we will move for the next part. It is the introduction to probability distributions. The probability distribution of a random variable x is a list of distinct numerical values of x along with their associated probabilities. A probability distribution is basically relative frequency distribution organized in a table. Here what we are going to discuss is we are going to have an idea regarding what is meant by a probability distribution. First of all, discussing on probability distribution, we will just have a look on this matter. Now, I will explain this using an example. Now, think on if you are having the, consider the experiment on rolling a die. Consider the experiment on rolling a die. If we are rolling a die and what we are going to have is let x be the number on the surface of the die. Number appears on the surface of the die will be the random variable we are considering. If you see the possible values of x, now what we can see is the possible values of x can be considered as 1, 2, 3, 4, 5 and 6. It is because since we are having 6 sides or 6 surfaces of a die, then we are having the numbers as 1 to 6. And if you roll a die for 6 times and we'll say the frequency we are getting the frequency. Suppose that we are rolling this die for, if it is unbalanced, we'll say this as an unbalanced die and we have rolled this die and we have obtained the frequencies as this. We have got 1 4 1 time, 2 4 3 times, 3 4 5 times, 4 we have obtained 2 times, 5 again 1 time and 6 is again 1 time. Now, if you need to obtain the relative frequency, suppose we have obtained the relative frequency, the way of obtaining relative frequency is first we need to get the total frequency. Therefore, if you get the count, here we can identify altogether there were 13 rolls. It is once you add these values, the total gives the value as 30. Then if you take the relative frequency, what you can do is you have to divide the frequency by the total value. Then we can say it is 1 over 13. Here it is 3 over 13. This one will be 5 over 13, 2 over 13, 1 over 13 and 1 over 13. If you see on this relative frequency, it says that the relative frequency of getting 1 is 1 over 13. Relative frequency of getting 3 is 5 over 13. Now think about if you are constructing a table including this x and the relative frequency. This relative frequency is said to be the probability of that event. Therefore, it is the simplest definition that we can give for the probability based on this table. Therefore, we can let this as relative frequency as probability of x having the small letter x denote the value of the random variable. Now we can see that the values of the random variable is this, and the probabilities of getting these values are now equal to 1 over 13. Here it is 3 over 13, 5 over 13, 2 over 13, 1 over 13, and again 1 over 13. Now you can see that here we are having the possible outcomes of x. It says that the list of distinct numeric values of x. Here we can see numeric values of x, what we are saying as the possible outcomes of this experiment for this random variable x, along with their associated probabilities. Now you can see in the second column the probabilities associated for each value is mentioned. Therefore, this type of arrangement is said to be a probability distribution. This type of arrangement is said to be a probability distribution. Therefore, when we are constructing or when we are obtaining a probability distribution, generally we can show it using a tabulated form, or else sometimes we are using or sometimes we are representing this in the function form. And when I'm discussing about this discrete and continuous probabilities, I will discuss some examples related to that as well. Therefore, generally we can say that probability distributions can be shown in the tabulated form, or else we can show it as a function, or else we can show this probability distribution as a function as well. Therefore, simply we can say that the probability distribution of random variable x is said to be the distinct numeric outcomes or the distinct outcomes of the random variable along with their associated probabilities. Therefore, the arrangement of the possible outcomes of the random variable along with the associated probability is meant to be a probability distribution for a random variable. When we are discussing about the random variables, we have identified that there were two categories of random variables, such as discrete random variables and continuous random variables. Since we can identify random variables as two categories, we will be able to identify probability distributions as in these two categories. Therefore, since we can have two categories of random variables, probability distributions also having it two categories. Therefore, there will be two categories of probability distributions. I will abbreviate it as probability distributions in PD. Here we can identify discrete probability distributions as well as the continuous probability distribution. Therefore, these are the two types of probability distributions that we can identify. Now we will discuss on the discrete probability distribution and continuous probability distribution. When we are defining on these categories, I told that based on the type of the random variable, we are defining the type of the probability distribution. Therefore, simply we can say that if you look on the discrete probability distribution, if x is a discrete random variable or the considering a variable or the random variable, if it is a discrete random variable, then we will get a discrete probability distribution for that random variable. If x is a continuous random variable, then we will get a continuous probability distribution for that random variable. First, we will discuss about discrete probability distribution and its properties. Here it is saying that let x be a discrete random variable, then the probability mass function of x is a function of fx, and it is denoted in this form. Fxi equals to px equals xi for the values of xi includes to the belongs to the set of x and 0 otherwise. If you see on these wordings, here what we have defined previously, if x is a discrete random variable, then it will have a discrete probability distribution. And when I am discussing about the probability distribution, I told you that we can represent the probability distribution in the form of an equation, or in the form of an equation in the sense form of as a function. If you obtain a function, the form of function for a discrete probability distribution, then such function is named to be a probability mass function for the random variable, and it is abbreviated as PMF and denoted by Fx. And please keep in mind that generally we are using the lowercase letter f to denote the probability mass function. Therefore, here we can say that probability mass function in this form, when the value of x becomes xi, for this function f, we can have it as probability that x equals xi, where xi belongs to x and 0 otherwise. It is quite in this form. Now think about the previous example which I have taken, rolling a die and taking down or noting down the number on the surface. Now we can see if this is the random variable x, the possible values, the first possible value is 1, 2, 3, 4, 5, and 6. Now we have identified the probabilities. According to the previous example, it was 113, 313, 5 over 13, 2 over 13, 1 over 13, and again 1 over 13. This is meant to be a probability distribution. Now we can again identify this as a discrete probability. This can be considered as a discrete probability distribution. It is because here we can see that random variable x is in the form of discrete random variable. That is why we can say this as a discrete probability distribution. Now, if I convert this probability distribution into the form of function, what I can take is here, since this is a probability mass function that I am taking, and I am letting this as fx, or else if you need, you can say it as xi. If you see about these are the this is the column x, and it represents the random variable, and the first value is stand for the x1. This is the value for x2, second value of x, then third value of x. Likewise, this would be sixth value of x. Then if you use a general form of denoting these values, this can be considered as the xi. That is meant by a value xi. Then according to this definition, we can obtain the probability mass function for this experiment, or for this as xi. Then this can be considered as probability that x equals xi, and it is where that xi belongs to set x and 0 otherwise. If you now try to convert this table into a function form, what will you get is, here you will have to, here you will have the values of x, and in this place you are asked to write down the values, so the probability, the associated probability values for each xi. Now you can see that there are 6 probability values, but there are 4 types of probabilities there. If you write down the values, then you can say that it is 1 over 13 is there, 3 over 13 is there, 5 over 13 is there, 2 over 13 is there. I write the values in this form. 1 over 13 is there, 3 over 13, 5 over 13, 2 over 13. And if you see about what are these probabilities, what are the values associated for these probabilities, then we can say that when x equals 1, 5 or 6, we will get the probability as 1 over 30. Here we can see that at this point we have obtained probability as 1 over 30. In this point, we have obtained probability as 1 over 13. In this place, we have obtained probability as 1 over 13. That is why we can say for x equals 1 or 5 or 6, we will have 1 over 13. The probability of getting these values as 1 over 13. 3 over 13, where we get x equals 2. Then x equals 3 for this value. Here we will get x equals 4. Now, if I ask about what is the probability of getting value as 7, probability of getting 7. Since there is no value on the surface of a die as the value 7, this event cannot be happen ever. That is why we are saying that this value is 0 otherwise. 0 otherwise, in the sense otherwise means any other value apart from these values will be included in this region, and for such values we will have the value of the probability as 0. It is quite as if it is 7, value is probability is 0. The getting the surface of the die having value 8 is again 0. It is because we cannot see any surface numbered as 8. That is why we can say the probability of happening such an event is equal to 0. That is why we can say we have to say otherwise this becomes 0. Therefore, the thing which explained using this equation is elaborated here. It is what we are saying as fx, and for the possible values of xi belongs to x, it means that the values of xi can be, or x can here, since I have used x, I have used x here as well. Since we can see for the values of x equals 1, 5 or 6, we can have the value as 1 over 13. For the value of x equals 2, we can have 3 over 13. Likewise, we may have the probabilities, and we can get 0 otherwise. If you consider another example, by considering on if this die is a balanced die, then what we know is we are having the equal probability of getting each side as the top surface of this rolling. If you see on that matter, now think on if it is a balanced die, then we will have the values as 1, 2, 3, 4, 5, and 6, and probability of getting x equals simple x, this equals 1 over 6, 1 over 6. Here we can see that all the values having the same probabilities. Therefore, we can say here we can say this is our fx. Fx equals 1 over 6. It is for the values of x below x equals to 1, 2, 3, 4, 5, and 6. And we have to say 0 otherwise. Now you can see the exact form in this way. Since we had several different probabilities, we have to use it in this way. Otherwise, if you are having the same probability, then you can write the probability, discrete probability function in this form, and 0 otherwise. When we are going to discuss about the discrete probability distribution, we have to pay our attention on these two conditions. This is the next important thing that we are going to construct on discrete probability distribution. These two properties should be satisfied, or these two conditions should be satisfied. The first condition is all these probability values should be greater than or equal 0. It means that they cannot be having any negative values. Therefore, we have to say that probabilities should be always non-negative values. That is mentioned in here. For fxi should be greater than or equal 0 for each xi belongs to set x. Here we can see that all the values for 1 to 6, we are having a positive value, otherwise it is 0. Here also we can see that there is no any negative value. The values associated for the probabilities associated for each value of x has a positive value, or else otherwise it is 0. That is the first thing that should be satisfied. Now think on this case, if we are having the value here as minus 5 over 13, this cannot be considered as a valid discrete probability distribution. It is because here one value is given as a minus value. Therefore, probabilities cannot have, since the probabilities cannot have minus value, always these probabilities should be positive values. And the next case is the summation of xi, where I goes from 1 to n, should be equal to 1. It means that summation of the probability should be equal to 1. It means that total probability should be equal to 1. If we are having an experiment, if we are performing an experiment, conducting an experiment, then the summation of all the probability values should equal to 1. It is the condition mentioning here, if xi equals to 1. If you see on this example, here 1 over 6 for 6 times, we got the total as 1. If you see about the total on this, it is 1 over 13, 3 over 13. And if you get the total, again, this should be equal to 1. If and only if these two conditions are satisfied, then we can say such a discrete probability distribution. And now we will move for the continuous probability distribution. I will just give you a brief idea regarding the continuous probability distribution. And at the beginning, it is stated that according to the type of the random variable we are having, we are defining the probability distribution as discrete or continuous probability distribution. Therefore, here, if you suppose that x is a continuous random variable, then we may have a continuous probability distribution. For a discrete probability distribution, we have defined a probability mass function abbreviated by PMF, but for the continuous probability distribution, we have to define the probability density function, which is abbreviated as PDF. And this is also denoted by Fx, and this says the probability of being in the region of A and B. Therefore, we can say this Fx denotes the probability being in this region, and it is generally calculated using the technique of integration. Therefore, if we are having the probability that x lies between A and B, is generally saying as integral of the function Fx with respect to dx for the region A to B. Therefore, this is how we can say it. And here also these two conditions should be satisfied. It means that all probabilities should be greater than or equal zeros. It means probability values should be non-negative values. And here we had the summation, but instead of summation, if it is becoming continuous, we have to use the integration. Therefore, if you see on the fundamentals of integration, it is actually made from the summation of the small areas. If you are considering a curve, that is why we can say that we have to integrate the function from minus infinity to plus infinity. This should be equal to 1. Generally, we are denoting it from minus infinity to plus infinity. It is because since this is general form, otherwise from the least possible to highest possible value, we have to integrate this function, and this should give the value as 1. This is how we are pay the attention on the continuous probability distribution, and continuous probability distribution should satisfy these two conditions as well. Now we will focus on the cumulative density function of a distribution. If you are going to discuss about the cumulative density function of a distribution, again, we are defining two techniques for differentiate as this discrete for discrete probability distributions and for continuous probability distributions. And when we need to find out the cumulative density function, you all know that in the previous stages, we have used this as the if this is the frequencies, Then we have obtained the cumulative frequency if it is x is 1, 2, 3, 4, 5. Suppose that we had the frequency set as 8, 7, 6, 9, and 5. Then we have obtained the cumulative frequencies as 8 comes as it is, then 8 plus 7, 15, plus 6, 21, plus 9, 30, plus 5, 35. This is equal to 35 as well. This is how we have obtained the cumulative frequencies. Now, we are using this concept for the probabilities to obtain this cumulative density function. Now, suppose that if x is given as, we will take the same example, px equals x, and here we are getting the probability. And if you need to obtain the cumulative probability, then we can say this as probability of x less than or equal x, and the concept that we have used here can be directly applied here as well. Then we will have the values 1, 2, 3, 4, 5, and 6. Probabilities are given as 1 over 13, 3 over 13, 5 over 13. I am using the same example which we have used previously, 1 over 30. Then if you need to take the cumulative probabilities, the first value goes as it is. Always we are considering the less than cumulative probabilities, not the greater than cumulatives. We are not considering here. Therefore 1 over 13. Then this 1 over 13 plus this quantity, it will become 4 over 13. Then it will become 9 over 13. Likewise, this becomes 11 over 13, 12 over 13, and it will now 13 over 13. Now we can see that at the as the last row, we are getting 13 over 13. This equals to 1. This is the next special thing that we can identify for the cumulative probability distribution. If it is a valid probability distribution, the last row should give the value as 1. Now, if you assign the x with this cumulative probabilities, then this can considered as a what we are saying as a cumulative probability distribution. Now, this says that the probability of getting a number less than or equal to 1 is 1 over 30. If you see on this value, it says that probability x less than or equal x. It means that if you consider up to this point, then the possible values of being x are 1 and 2. Therefore, we can say that the probability of getting 2 or a value which is less than 2 is 4 over 30. It is just the summation of these two values. Now, if you consider on this point, it says that the probability of getting 4 or a value which is less than 4. Therefore, you have to take the summation of these 4 probabilities. This will give the value as 11 over 13. Likewise, we can obtain the cumulative probability distributions. Since this is a discrete case, we have taken the summations, but if you come for the what we are saying as the continuous case, then instead of summation, you have to integrate the function for the given region. And the next thing is we are using lowercase letter f to denote the probability mass function, or what we are saying as the probability density function in the continuous case. And we can say that uppercase letter as fx, this is to denote the cumulative density function for both for the discrete case or the continuous case. Always we are using this uppercase letter fx. Therefore, we can simply say for the discrete case, we can define this fx. We can define the fx, the summation I goes from 0 to xi for the fxi. If it is a continuous case, then we can say it is fxi. Then this can be obtained as integrating from minus infinity to fxi, fx with respect to dx. For this, this is for the discrete, and this is for the continuous. And now we will discuss an example on this discrete probability distribution. We will see on how to construct the probability mass function as well as the cumulative probability distribution. Here it is saying that a student has tossed a coin for three times, and values on the surfaces were noted. Therefore, if a coin we are taking, there will be two outcomes. If it is we'll say this coin as a balance coin, therefore probability of getting head is half, probability of getting tail is half. Now this is for a single coin. Now think about if the coin is tossed for three times, then it is now quite like tossing three coins. Same coin tossed for three times. Therefore, we will get a value having three digits, or three values would be there for a single outcome. Therefore, from the first coin, we may get the head. At the first toss, we may get head, and again head with another head, or else we may get head, again head with the tail. Then head can be obtained as obtained along with tail and another head. Then head can be again obtained with another tail and tail. Now here we may get tail in the first toss, and again two heads. Then tail with head and tail, tail with tail and head, tail with tail and tail. If you toss a coin for three times and noted down the surface obtained, then there would be 8 possible outcomes. Now you can see these 8 possible outcomes has now included in the table in the first column, and we are assuming that it is a balanced coin. Here it is given as a balanced coin as well. Since it is a balanced coin, the probability of getting each outcome should be equal. Now you can say that altogether there are 8 outcomes. Therefore, 1 over 8 would be getting the chance of each of these outcomes. 1 over 8 is getting the chance of each outcome. Then we can say that we have obtained the probability of getting each event as 1 over 8. Therefore, if you simply consider these first two columns, then it will be your probability mass function. Here it is in the tabulated form, or else you can write down it as the fx. Fx would be now equals to 1 over 8 for x belongs to set x and 0 otherwise. Now we have to say that the possible values of x in the set x, these are the values we are getting: head with tail. Likewise, we have to include all the 8 possible outcomes in this set x. Therefore, if our set here we'll let this x, rather than using the same type, I will use this way. Here it is lowercase letter x, and it says that lowercase x belongs to set x. Therefore, if this is the set x, then lowercase letter x denotes for each value of this possible outcome. That is how we are getting 1 over 8 for this and 0 otherwise. Therefore, this since we are getting the equal probabilities, we can have this. And now you are supposed to obtain the cumulative probability, and cumulative probability we are obtaining the less than cumulative probabilities. Therefore, this value would be 1 over 8. Then it is added to next 1 over 8. Likewise, we have obtained this cumulative probability distribution. Now you can see at the last row, we are having the value as 1. It is just the 8/8 denotes as this 1. Now this is the cumulative probability distribution for this. And if you need to obtain the cumulative density function, what we can do is we can, this has fx, and we may have set of values starting from 1/8, 2/8, 3/8. 8/8. Then we have to write down when x less than or equal 1, we will get this value. When x less than or equal 2, we may get this. Likewise, we can fill up these values. And here it is x less than or equal 8. That is how we are getting the values. Therefore, this is what we can say the cumulative density function for this given experiment. Now it is shown in the graph as well. Here we can see that since we are getting equal probability for each situation, we are getting it just as a line here. Since we are having the probability as 0.125 is the value here, which equals to 1/8. Now here we can see that the cumulative density function is going in this way. And you can see that the highest value for this is now equal to 1. And now we will move for the last part of this, obtaining the expectation of random variables expectation. And here we will discuss about the obtaining the variance and standard deviations as well. There is a concept called moment for a random variable in statistics. Then using that concept, we are going to identify the expectation of a random variable. And based on whether the random variable is discrete or continuous, we are using two techniques, simply saying as summation and the integration techniques. Summation for discrete case, integration for continuous case. Suppose that x be a discrete random variable, and if x can take the values in, we are calling it is belongs to set D. And if the probability mass function, if we write down all the necessary details here, x belongs to set D, and probability mass function is denoted as fx. And then you are asked to calculate the expected value. Expected value, in other words, we can simply say it is the mean value for the random variable. Expected value is said to be the mean value, and it is obtained using the first moment for a random variable. Therefore, generally we can say that mean is denoted by mu, and since it is the same term for expected value, we can see this as the expected value of x. Then expected value of x can be obtained as the summation of x times fx, x times fx, where x belongs to set D, where x belongs to set D. Using this equation, we can obtain the mean value for a random variable. Means x times fx over this all the possible values of D. And if it is for a continuous case, what we can do is mu can be obtained as, instead of this summation, what you can do is you have to integrate the function from minus infinity to plus infinity. Generally, we are using this as notation only, but in the actual situations, what we have to do is here we have to substitute, instead of minus infinity, we have to substitute the exact lower limit, and here we have to substitute the exact upper limit. Then we can obtain this as x times fx, and then we have to integrate with respect to the subject x. That is how we are getting the mean value or the expected value for a random variable. And this is said to be the first moment of a random variable. And now we will discuss how we can obtain the variance of a random variable. If you are taking the same concepts, the same same notations, x belongs to D, and here the probability mass function is given as fx for the discrete case, and PDF is same as fx for continuous case. And if you ask to obtain the variance, variance is said to be the second moment around the mean for a random variable. Therefore, we can say this as, generally we are denoting this as the sigma squared. Generally, we are denoting this as sigma squared, and sigma squared can be obtained as the expected value of x minus mu to the power 2. Here we have to take x minus mu to the power 2 and its expectation. That is, if I write it in this way, it would be clear for you. Expectation of x minus mu to the power 2. And if you solve this, if you are going to obtain this quantity, what using the same concept as this, we can obtain this sigma squared. This as, here if you are having E with the bracket, if it is x, we have written it as sigma x times fx. But here instead of x, what we are having is x minus mu squared. Therefore, now what we are going to do is sigma x belongs to D. Here we are using this x minus mu squared here. X minus mu squared times fx is used. This is for the discrete case to obtain the variance. And if it is in this continuous case, then we have to integrate this from minus infinity to plus infinity. X minus mu squared times fx dx. Using this equation, we have to obtain the variance for the continuous case. This is how we are obtaining expected value and variance. But when we are going to obtain the variance for random variables, here we are just discussing it for the discrete case only. We are not going to define this. We are not going to discuss this for the continuous random variable. Therefore, in simply what we can use is, instead of using this equation, we can simply obtain the variance in this form. It is just as the ex squared minus ex to the power 2. This is the way that we can easily obtain the sigma squared. To obtain the ex squared, what we can do is, we can just have the summation of x squared fx. And we all know that, already know that ex is given as summation of x times fx, which we have already identified as mu. Therefore, using this concept, we can easily obtain the value for sigma squared. And in this session, we will discuss an example for the discrete case. And anyhow, you can, if you are defining, this equation can be again used for the continuous case as well. If I brief about that as well, if it is ex squared, then this will become minus infinity to plus infinity x squared times fx dx. And we have already identified that ex equals to minus infinity to plus infinity x times fx dx. Using these two, you can you can obtain the values, and then you have to substitute it to this equation to obtain the value for sigma square. Oh, this is what I have mentioned here. It is now given in these wordings. Now we will discuss an example related to this obtaining mean and variance for a discrete probability distribution. Here it says that data was collected over 200 days by tabulating the number of calls in a day incurring for a technician for a machine repair in an industrial zone. It says that the first column says the number of calls received per day for incurring for a technician for repair, and the second column says that number of such days obtained this number of calls, or number of such days obtaining this. Then it is quite, if I explain about this data set, here it says that there are 30, for a day, there were some days obtaining, getting 36 calls, and there are 5 such days. If you see on the second column, there are some days having 37 calls they got for inquiring for a technician, and there are such 10 days throughout this 200 days. And if it is for the last row, there are some days they got 45 calls, and there are such 15 days of obtaining or getting 45 calls. And the total of these days should be equal to 200. It is because they have considered, or they have just observed it for 200 days. And suppose that these are the only thing you have given, and you are asked to calculate the mean number of calls, and suppose that these things are not given for you. Suppose that this part is not given for you. The only thing it is given for you is the number of calls received and number of days, number of such days. Then you are asked to calculate the mean number of calls in a day inquiring for a technician for machine repair. Here, first they are asking about the mean number. If you need to obtain the mean number, what you need to know is obtaining mean number is the expectation. This equals to summation of x times fx. In simply, fx is simply we are having this as px equals to x. Since this is an example I am taking, I will just explain obtaining the this PMF, or the here what we are saying as this as the probability mass function. And then I will discuss about the obtaining cumulative density function as well. And then we will move forward obtaining these values. To obtain the mean value, I told you that we need to get the summation of this x times fx. Here still we do not know what is the value of fx. Therefore, we need to identify the value for PMF. Then what we can do is we can just get the relative frequency. Here we can get the relative frequency. Relative frequency can be obtained. This is what we are saying as the probability that x equals to xi. The relative frequency for first one would be 5 over 200. The next one is 10 over 200. Frequency divided by total, again 10 over 200, then 20 over 200, 25 over 200, 30 over 200, 35 over 200, 25 over 200, another 25 over 200, and at last it is 15 over 200. Here, rather than using a fraction, I have just used the decimals in the wordings. Anyhow, I have used the fractions here. Now, this can be considered as this Px equals xi. This is what we can say as the probability mass function. And then we can obtain the cumulative density function as well. Cumulative, instead of cumulative density function, I would like to say this as, rather than that, probability x less than or xi. Then what we can do is, here it would be 5 over 200. Then the plus this quantity, it would be 15 over 200, 25 over 200. Likewise, we may get the value at the end. For the last row, it would be 200 over 200, which equals to 1. Therefore, this is what we are getting as the cumulative densities. And then what we have to do is, this is, I have just shown how to obtain these two. And then what we need to do is, actually the question asks us to calculate the mean value. Calculating mean value requires this quantity x times fx. Here x times fx means x times fx is the quantity we need. Instead of x times fx, what we can do is we can use it as x times p, x equals x. This is what we have used as fx. It is because we have defined that fx equals to px equals x for x belongs to set x, or else 0 otherwise. Since we have performed it in this way, instead of fx, we can use this quantity. Then what we have to do is, our x is 36, then 36 multiplied with this quantity. Likewise, you have to obtain this this column. And if I perform one calculation, here it is 36 into 5 over 200. Therefore, what we have to do, first row obtains as 36 multiplied with 5 over 200. If you perform this calculation, simply what you have to do is 36 multiplied with by 5 and divide by 200. Here you will get here it as 180 over 200. Likewise, you may have to perform the calculation. If I do the second one, it is 37 multiplied with 10 divided by 200, then it would be 370 divided by 200. Likewise, you may have the values. Then you have to obtain the summation of these values at the end. And this is, here what we are getting is summation x. Here what we are getting is summations x times fx. This is equal to what we are expecting as our answer. It is for the mean value. Therefore, if I show the answer for you, then you can see that the summation, the multiplications give this set of values, and the summation has now obtained as 41.30. Therefore, we can interpret on this result as averagely for a day they are getting 41.3 calls for asking for a technician for a machine repair. Likewise, we can obtain the mean value, and you can obtain the variance for this example. To obtain the variance, what we need is, here what we have to do is, we can use this equation rather than using this x minus mu squared fx. Rather than using this equation for the sigma squared, it is better to use the equation ex squared minus ex to the power 2. It is because now we know the value for this quantity. It is as 41.3. We already calculated this expected value of x as 41.3, and now we need to obtain this ex squared quantity. Ex squared can be obtained using what we have learned was summation of x squared times fx or px. Now we have to construct this quantity in our table. Therefore, what we can do is, suppose that this is the quantity we are having, and here what we are going to do is, we are going to construct the new column. New column says that we need to obtain this x squared fx. Therefore, first we need to identify a column for x squared, or else if not, you can directly obtain this column x squared times px equals xi. It means that the first column should be x squared and multiplied with the third column. First column should be squared and multiplied with the third column. Then you will get the values at this point. Therefore, as an example, if I do the first row, what you get is, you have to square 36 it means 36 into 36, and then you have to multiply it with the 5 divided by 200. Therefore, if you perform this calculation, you will get 32.4 in the first row. And if you perform the similar thing for the second row, it means that you have to have the square term of 37, and then you have to multiply it with the probability is 10 divided by 200. Then this value would be 68.45. Likewise, you can perform this calculation, and here you may get the summation of x squared times fx. These summations, we will say this value as a, then you can substitute this value here. This is what we are getting as the ex squared is equal to summation of x squared fx, and you can perform that substitute. You can do that substitution and perform the calculation according to calculate the value for sigma squared or the variance for this example. And this is all what I need to discuss in this session, and thank you all for being participating for this session.